Hi everyone. Today we continue with calculus after 2 weeks. Again, Süleyman Üstünel is our lecturer from Bilkent University. And as you know, all documents are in our website, and please visit there. And that's all from me. Hocam, we can start.
Okay, you give me screen power.
Now you can share.
Okay, good. Okay, so we shall today make some, let's say, novel applications of what we have seen as integration theory. So I will first tell you, I will just recall what we have learned up to now. There is not too many things, but it's good to do. Okay. So we have learned how to define abstract integration with respect to a probability measure. So we have taken an omega fp space and we have defined a random variable to be a function from omega to real line. It's called a real random variable if inverse image of any open or closed interval AB belongs to F. For any A less than B, it suffices that A and B to be rationals from a theorem. Okay, I am just putting the things in a practical way. Then if X furthermore positive, then we have defined integral of X as the limit of the integral of step functions as n goes to infinity, where xn are simple or step functions which are increasing pointwise to x of omega, and such a approximating sequence of simple functions do exist thanks to the measurability property of x. Okay, this thing implies this possibility, this constructibility, and we have shown that this limit of the integrals is independent of the approximating sequence xn. If xn, instead of xn, I take another sequence yn, which is also increasing to x, then it gives the same, their integrals, limit of their integrals gives the same result. Okay, hence this thing is a well-defined integral. And we have proved as a consequence of this definition two important theorems. The first one is monotone convergence theorem, says that if xn is a sequence of random variables, not necessarily simple, which are increasing to a random variable x. Increasing means for each omega, it's a monotone increasing sequence. So it's pointwise convergence, the most stupid convergence of literature, okay? Then we have seen that we can commute expectation, limit of the expectations of xn or integrals. I call it them expectation by professional deformation. This commutes with the integral. This is called monotone convergence theorem. Okay, and as a consequence of this, combined with Fatou lemma, we have proven dominated convergence theorem, which says the following. Now, we are already getting out of the monotone convergence result in dominated convergence theorem. It says the following: assume that, let me change the notation, Zn is a sequence is a sequence of random variables such that Zn are converging pointwise to some Z. So this is pointwise convergence. Now, if there exists a random variable y, positive random variable, such that its expectation is finite, and that it also upper bounds absolute value of all Zn's, Zn of omega in absolute value less than or equal to y of omega for any omega and n, then the conclusion is that first, the Zn's are integrable, so it means that absolute value of them have finite expectations. Then this is trivial consequence, but nevertheless, I will write it. I say that Zn belongs to L1 of these are integrable random variables. To limit as n goes to infinity, Zn dp is equal to Z integral of Z dp, and in fact, of course, in fact, expectation of absolute value of Z is also finite. And finally, this is the strongest claim, is that limit as n goes to infinity, integral of absolute value of Zn minus Z dp is equal to 0. In fact, this, of course, implies this. Okay, so this is called dominated convergence theorem. Okay, and we shall today. I have the intention of making some non-trivial applications of this to strong law of large numbers and some ergodic theorems. You shall see these things are very natural, but they are not easy to prove. First, I would like to give an example of a probability space which is implemented in all your computers. So I will take example of probability space. This is a basic example, hence I will give it explicitly. I will make no proof of it, but this is standard. You can find it in any real analysis book. For instance, you take the book of Bartel, real analysis, or the book of Rudin, again, Rudin, real and complex analysis. These are classic books of analysis, real and complex analysis. These two books, I strongly recommend you to have them in your library. Okay, so I would like to construct a probability measure on the interval 0, 1. So let omega to be 0, 1 interval. Okay, so I will define if AB is an interval, is I, then the measure of my interval I will define as to be just the length of the interval, B minus A. Now, I will denote, this is the, I am giving you exactly the construction of Lebex, by the way. Okay, so if A is any subset of the interval, so if A is any subset of interval, I didn't say measurable, whatever, okay, then I define lambda star of A This is called an outer measure. This is a standard construction. This is the infimum of the sums with respect to n of lambda of in such that in union of in covers A. And I am taking infimum with respect to all covers of in. Okay, so infimum is taken with respect to all open covers of A. Open cover means open intervals whose countable union is a superset of A. Okay, this is the definition. So this is a standard definition, and Lebex has made the same construction. So the thing is that we say, I didn't speak anything about the measurable sets. We say that a subset, so B subset of the unit interval AB is 0, 1, sorry, is called lambda measurable if when you look at the lambda of B, lambda star of B, sorry, so outer measure of B, sorry, this is not like that. So if B is called lambda measurable for any A subset of the interval 0, 1, we have outer measure of A is equal to outer measure of A intersection B plus outer measure of A intersection B complement. This is the definition of lambda measurability. Okay, I will come to the relation with respect to measurable notion that we have obtained before. Okay, and the theorem, the big theorem of Lebex says that this lambda measurable sets is a sigma algebra on 0, 1. This is the first property. Secondly, if you look at the outer measure lambda star restricted to this lambda measurable sets, let me denote their set M sub lambda. Its restriction is a sigma additive probability measure. And thirdly, in fact, this where, okay, M lambda is the set of Lebex measurable sets. Lebex or lambda measurable sets. And finally, the Borel sigma algebra of the interval 0, 1 is a subset of M lambda. And the difference is that M lambda contains the negligible sets, but Borel sigma algebra may not. Okay, so in fact, if I add to B of 0, 1 all the lambda negligible sets, then they are equal. Okay, so this is a solid example of what we have done up to now. Okay, and the integral with respect to lambda is precisely what we call the Lebeck integral on the interval 0, 1. And the same stuff works on all the real line. So extension of this, we can replace 0, 1 with either close interval 0, 1, the difference is a negligible set, or with R. But in the latter case, in the case R, we have no more probability measure, but this is what we call Lebeck measure. This is the extension of the measure that with respect to which you integrate continuous functions in calculus. Okay, lambda star is not a probability measure. But it is, again, a sigma additive positive measure. And all we have done works with it also, the dominated convergence theorem, etc. Okay, but I prefer to work with probability measures because I have explained to you Lebeck measure in infinite dimension does not exist. So it is not necessary that I lose one time with a finite dimensional unbounded Lebeck measure. It's a loss of time. Okay, so for instance, then I can give here very solid examples about the dominated convergence theorem. Okay, for instance, let me give you a situation where you have a sequence of random variables which are converging to 0 point-wise, but their expectations do not converge. Okay, so a counter example to dominated convergence theorem if one of the hypotheses is not satisfied. Okay, so let xn be the indicator function of the interval, let's see, 0, 1 over n times t times n. Okay, so if you look at the value of xn for a fixed t as limit n goes to infinity, so this means that I am looking for those t's. I mean, the t should be such that it should be less than 1 over n for any n for the result to be non-zero. Okay? There is no t like that, hence this limit is 0. But if you take the integral of xn t with respect to Lebeck measure, dt, this is a crazy notation, it will give you always 1. Because it's the length of interval multiplied by n, it is 1 over n multiplied by n, it is equal to 1. Okay, so as you see, then limit does not commute with the integral. The reason is that, well, we have no domination. The reason is that xn is not upper bounded. Okay, xn is not bounded, upper and lower bound, by an integrable function or random variable. Okay, this is a standard counterexample to the dominated convergence theorem. When the hypotheses are not satisfied, you may have catastrophe. Okay, so think about it at home. Okay, now once that this is settled, let me give give some side benefits of these theorems. I have touched a little bit last time, but I was a little bit sleepy last time, so I'm not sure if this has been really realized, I mean, appreciated. So let me come to the general case. So general case. So we are in the situation omega fp. F is a nice sigma algebra, P is a countable additive probability on it, with respect to which we have defined integration, and for which then we know monotone convergence theorem and dominated convergence theorem. Okay. So the first proposition is the following. Assume that X is a positive random variable. And that A is a measurable set with zero probability. This may happen without A being empty. Look, for instance, at the case of the Lebex measure on 0, 1. You take any countable subset of 0, 1, it will have zero length, okay? So this, although it is not empty. Then the theorem says that expectation or integral of X multiplied by the indicator function of A is equal to 0. This intuitively, I'm not sure if it is clear intuitively. Well, in France, when I teach, the students were always troubled with this, and it is easy but not trivial to prove it. Okay, the proof uses monotone convergence theorem. So let Xn be a sequence of step random variables, so simple functions, increasing to X pointwise. Okay, then I know that in this case, Xn indicator times indicator function of A also increases to X indicator function of A. Hence, from monotone convergence theorem and by positivity, I know that limit of expectation of Xn times indicator of A is equal to expectation of X times indicator of A. I claim that each of this is 0. Why? Well, it is very simple. Because Xn is a step function and it is finite. It can be written as some finite sum of constants times indicator function of subsets of omega, which are measurable, hence multiplied by indicator function of A is equal to lambda I times indicator function Ci intersection of A, hence its expectation is equal to sum of lambda I times probability of Ci intersection A. Since A is 0 probability, this is 0 also, hence this is 0. So we are done. As you see, once that you can, you think to the definition of the integral and approximability of positive measurable random variables with simple random variables, this is trivial. But these two considerations that we have used, they are very sophisticated things because they come from sigma additivity. Okay, so you cannot teach this to the first year calculus students. It's impossible. Okay, that's why the French students were suffering when I was asking this as a question. Okay, so as a consequence of this, then I will define, so a consequence of this. Consequences of this observation. First, a definition. I will say that if x and y are two real-valued random variables, then I say that x is equal to y, p almost surely, if probability of the set omega on which x are different, x and y are different, this is 0. So, corollary of the above proposition is the following. So let x be positive, real random variable, or integrable, it doesn't matter, it is the same thing, and assume that y is equal to x, p almost surely. Okay, then expectation of x is equal to expectation of y. Okay, so it means that if x and y differ from each other on a set of probability 0, their expectation does not change, they are equal. Okay, so this is, well, once that you know the above theorem, it is easy, because let me write the set B, the set of omega on which they are equal, in such a way that from hypothesis probability of B is equal to 1, hence probability of B complement is 0. Okay, then trivially x times indicator of B is equal to y times indicator of B. It is not almost everywhere, this is everywhere. Okay, hence this implies that expectation of x indicator B is equal to expectation of y indicator B. Okay, and what is the difference between x minus x times indicator of B? This is equal to expectation of x times 1 minus indicator of B, which is equal to expectation of x times indicator of B complement, which is equal to 0. From the proposition 1, okay, from proposition 1. Similarly, if I look at the expectation of y, this will be equal to expectation of y times indicator that y is greater or equal to 0, because this set has probabilities equal to 1, hence it is complement is of probability 0, and I apply again proposition 1, okay, and this is equal to also, since this set intersection with B is again has probability 1, this is equal to indicator then y greater or equal to 0 intersection B, and on B y is equal to x, hence this is equal to x times indicator y greater or equal to 0 indicator B, and this is equal to expectation of x, since this thing has probability which is equal to 1. Okay, so it's then we see then that equality almost everywhere of two random variables respects the value of their expectations. So that's why I will define, okay, this will give me a definition. I will denote by L1 of omega fp, or simply sometimes, if I am too lazy to write all the notations like that, this is the random variables, their equivalence classes of random variables, such that, so this is the equivalence class, such that any x and y in this for any x and y in this, x is equal to y, p almost surely. Okay, so for instance, if I choose one random variable given point-wise defined, and I add to it indicator function of a set of 0 probability, they are still in the same equivalence class. Okay, and both of them, when they are in the are then in this set, and their expectation is equal to each other. Their expectations are equal. Okay, hence it means that this thing, if we denote by L1, without take all the random variables with finite expectation, expectation in absolute value, then strict L1 P is the saturation of this set with respect to equivalence classes defined here, like that. Okay, so this is an equivalence relation. It's an algebra exercise, I believe, to you, and the saturation of this random variables with respect to this equivalence class is denoted by L1B, strict L1. And an important observation is that L1 of P is a vector space. And in fact, if we define for any x and y in it, we define the distance between x and y as to be expectation of the absolute value of x minus y, then this thing, d, is a distance. It's called a metric, and it satisfies triangle inequality. It is trivial. It means that soon I will neglect writing these brackets like that. Okay, this is never used except with the novice people. After some time, we drop this notation because it is too heavy. Dropped notation. Okay, so let me show that this is a distance, for instance. If you look at the distance between x and z, so this is equal to expectation of x minus z in absolute value. Well, if y is another integrable random variable, then I can write this as expectation of x minus y plus y minus z. Then since this absolute value is